Welcome to the deep dive. Today we're digging into something pretty interesting. How college-level math, specifically integration, well, how it shows up in your everyday life, like in the food you eat.
Yeah, it's a great example. This deep dive is really for anyone curious about how calculus, differentiation and integration connects to really practical fields.
And our mission today is, well, pretty clear, isn't it?
It is. We want to unpack how integration is used in food security. Specifically, we're looking at total heat transfer during pasteurization. It's all about understanding the math that keeps our food safe.
Exactly. Like when you grab that carton of milk or juice, there's some serious science, some calculus actually baked right into making sure it's safe to drink. It's kind of amazing.
And the source material we're looking at focuses right on this. Integration in food security, total heat transfer in pasteurization. It's where the mathematical theory really meets a critical need, public health.
Okay, so let's talk pasteurization. We generally know it uses heat, right, to kill off bad microbes. But why is calculating the total heat transferred so important? Isn't just, like, checking the temperature enough?
Not really. It's a good question, though. Think about it this way. Killing microbes effectively isn't just about hitting a certain temperature for, a split second. It's about delivering enough total heat energy over the whole time.
Ah, yeah.
Too little energy, even if you hit the right peak temp briefly, it might not be enough to kill everything resistant.
Hmm.
But too much heat for too long. That can affect the taste, the nutrients. You need the total amount of heat energy delivered, the cumulative amount.
Cumulative, right. But I imagine the rate heat transfers, it's probably not perfectly constant, is it? Like throughout the whole
That's
process.
exactly the point.
The heating system temp might wiggle a bit, maybe the milk flows faster or slower, or even the starting temperature of the milk could be different sometimes.
Precisely. The rate of heat transfer, think of it as the sort of instantaneous heat power being delivered. That rate can definitely change over time. Let's call it RT, where T is time. Now, if RT was constant, sure, you could just multiply. Rate times time equals total energy. Simple.
But it isn't constant.
Yeah,
So simple multiplication is out.
exactly right. And that is where integration becomes, well, essential, indispensable, really.
Oh,
Integration is the tool we use in math to sum up something that's changing over an interval.
okay.
So here, we integrate that instantaneous rate of heat transfer, RT, over the entire time the pasteurization is happening, conceptually. You're finding the area under the graph of that heat transfer rate plotted against time.
So you take this like potentially wiggly line showing the heat rate going up and down over time, and the integral tells you the total energy transferred underneath that whole curve.
That's it exactly. It gives you the precise total thermal energy delivered. And this total energy, this number, is critical. It directly links to what's called the thermal dose, or often in the industry, the F0 value.
F0 value.
Yeah, F0. It basically quantifies how effective the heat treatment was.
Hmm.
Comparing it to holding the product at a standard high temperature, like 121.1 Celsius, for a certain equivalent time. It's a standard measure of lethality.
Wow. Okay. So the number you get from doing that integral, that total heat energy, that F0 value,
Yeah,
that's what engineers look at to say, yep, this batch is safe.
absolutely. That's the metric. They calculate that F0 value, which comes straight from integrating the heat transfer rate, and they check it against the safety standards for that food. It's really the mathematical proof that the process worked, that enough thermal energy got delivered to kill the pathogens, even when the rate wasn't constant.
So without integration, they couldn't actually be sure if the rate was variable.
They couldn't be nearly as accurate, no. It provides that necessary precision.
And that's the connection for you, listening. That calculus concept, finding the area under a curve, summing things up. It isn't just a problem in a textbook. That operation, using integration, leads directly to that F0 value. The thing that guarantees your milk, your juice, is safe. It's fundamental to food security.
It really shows how these, sometimes abstract-seeming math concepts become vital tools for public health on a huge scale. It's the math standing between safe food and potentially unsafe food.
So let's boil it down. What's the key takeaway here?
Simply put, integration gives engineers the power to accurately calculate the total heat energy needed for effective pasteurization, often measured as that F0 value. And that calculation is absolutely crucial for verifying food safety. It's a core part of our food security system.
It's a fantastic illustration, really, of how the math you might be learning or learned years ago has these really important, often hidden impacts on your daily life.
Yeah.
Foundational stuff.
Yeah. And maybe that leaves you with something to think about as you encounter more math, maybe more complex tools. Where else might they be working quietly behind the scenes? ensuring safety or efficiency or quality in parts of the world around you that you've just never considered before.